tip-jet-driven rotor. The advantage from the engineering point of view is that it completely eliminates all of the mechanical transmission.
The Gyrodyne was modified to fly as a compound helicopter. It took off and landed under the power of its rotor system, but in forward flight it flew as a gyrocopter. The tip-jet-driven rotor worked by taking air from two auxiliary compressors and combining it with kerosene in a combustion chamber at the end of each rotor blade. This mixture burned to produce the thrust that spun the rotor during takeoff and landing. Twin propellers mounted on the stub wings provided forward thrust and yaw control, and the tip-jet-driven rotor incorporated cyclic and collective pitch. In forward flight, the power of the tip jets was shut down and the rotor provided lift through auto-rotation. By the mid-1950s, takeoff, landing and transition to forward flight as a helicopter had been achieved. Although it could only sustain level flight as a gyrocopter for a short period of time, its success motivated Fairey to commit to 2 tip-jet drive projects.
Well, there are always engineering problems in any design. Of course, the first thing is that one had to provide a means of propulsion at the tip of a blade. The first thing you have to do, of course, is to get the air there together with fuel to provide a combustible mixture to provide the thrust for the tip-jet engine. So consequently, we had the problem of ducting all of the air through the centre of the rotor head, through the flapping hinge and the mechanical complexities of providing a flexible joint which didn't leak. And of course you had at the tip-jet a combustion chamber which was subjected to all of the centrifugal loading that comes on any element that is attached to the tip of the blade. There was a problem of, in fact, obtaining an outside shape which was adequate from the aerodynamic point of view, and obtaining an inside shape which met the needs of the thermodynamicists.
They learnt a great deal about some of the problems they were going to meet on the Rotodyne with the jet gyrodyne. And in the meantime, they then embarked on another little project, which was the Fairey ultralight helicopter, a little two-seater, like a little glass bubble, the sort of thing that you used to see in some of the science fiction magazines of those days, where people were racing around in their own little private helicopter. That one was tip-jet drive, so no torque problems, and the only thing they had to do with that was to make sure they had a directional control. And the way they achieved that was they had a stainless steel fin down into the jet efflux, which deflected the jet efflux to get yaw control. John Morton used to demonstrate that at Farnborough, landing it on the back of a lorry, coming down in auto-rotation and then flaring out at the last minute with power still on, and just flare it back onto the back of this flatbed truck.
The ultralight was built for operation from small ships with the Navy. 3 of the nimble little aircraft were built. They completed a 4-year comprehensive test program, including trials at sea and civil certification. But the project was abandoned in 1959 when the Air Ministry decided that larger helicopters would be needed by the services. A larger and more ambitious project followed the Gyrodyne at Fairey as well. It was called the Rotodyne. Fairey began preliminary development on this aircraft in 1946. Their success with the jet Gyrodyne and British European Airways' interest in a rotary-winged airliner helped push the project forward. In 1953, the Ministry of Supply awarded a contract for a single prototype aircraft. It would combine the takeoff and landing capabilities of a helicopter with the forward speed of a gyrocopter and the passenger capacity of an airliner.
Now, Rotodyne itself, of course, was quite an ambitious project. It was to produce a full-scale 40-seat airliner. The main thing was that it was a significant step forward to try and introduce airliner flight into helicopters. Everyone had the idea that you'd be able to fly helicopters straight into the middle of cities.
There was also a general desire in the government to promote research projects with limited expenditure in the terms of tens of millions rather than hundreds of millions. And I think the two things came together.
The Rotodyne resembled a stub-winged turboprop airliner with a 90-foot diameter rotor mounted on its top. This rotor was powered by tip jets. For flight in a helicopter regime, the tip jets were fed air from compressors that ran off its two wing-mounted Napier Eland engines. Fuel was mixed with this air and fed to the combustion chamber at the end of each rotor blade. Once the fuel and air mixture had been ignited, the burn was self-sustaining. The centrifugal force of the spinning rotor kept the fuel flowing to each tip jet. The air compressors at each engine fed two of the four tip jets. Thus, any engine failure would not result in a full loss of power to all four rotors. Once liftoff and forward flight had been achieved in the helicopter regime, the tip jets were shut down and power was transferred to the Napier Eland engines. The Rotodyne then flew as a gyrocopter. The turboprops provided forward power and the rotor provided lift in auto-rotation. Wind tunnel tests on a 1/6 scale model without a rotor assembly were conducted to establish the lift-drag characteristics under fixed wing conditions. An additional 200 hours were spent testing a 1/15 scale model with a powered rotor 6 feet in diameter to establish the effect of the downwash from the rotor on flight characteristics. As there were not yet any airworthiness requirements for an aircraft like the Rotodyne, Fairey chose to meet the industry requirements for both helicopters and aircraft. Design work was based on the specifications laid out in the British Civil Airworthiness requirements for helicopters and those for fixed-wing aircraft of comparable size and performance. Gaps between the two sets of rules were covered to the best of the engineer's ability in an effort to meet any future requirements established for compound helicopters. Fairey Aviation wanted to make the Rotodyne a commercially viable vehicle rather than merely a prototype. The 58-foot-long fuselage was assembled at the Fairey facilities in Hayes. This main body of the aircraft was then trucked to the company's factory at Stockport for final assembly. At Stockport, the Rotodyne's wings and turboprop Napier engines were installed. The twin tail fins and huge rotor were attached as well. Research and development onto the rotor system had been ongoing at the company's White Waltham facility since before the Jet Gyrodyne project. Now, after more than 10 years of research into tip-jet propulsion, it was almost time to flight test the gigantic compound helicopter known as the Rotodyne. It was certainly large enough to fulfill both the military requirements of the Air Ministry and the perceived need for air transport from city centre to city centre. 50+ passengers could be accommodated as per BEA's stated requirement. However, the question still remained: would it fly?
We announce the departure of Rotodyne flights to Brussels and Paris.
The Rotodyne's flight system was developed through Fairey Aviation's Jet Gyrodyne project. It utilized a powered rotor for vertical flight and propellers, short wings and the rotor in auto-rotation for forward flight. A huge 4-bladed rotor was chosen for greater reliability. It was essentially an all-steel structure. The rotor head contained 2 concentric ducts that delivered compressed air from 2 wing-mounted turboprops to pairs of rotors. The 45-foot-long blades carried fuel and air to combustion chambers at their tips. Driving the rotor blades at their tips eliminated the torque and gearing problems associated with such a large rotor. In this case, gearing that would have had to handle 6,000 horsepower. The entire assembly was attached to the top of the Rotodyne by a four-legged tower, which was covered with an aerodynamic nacelle. The propulsion system was mounted to the tip of each rotor blade and was fabricated primarily from nickel alloys.
One of the keys to the success that Fairey had with tip jets was that they did some very serious ground development work before they ever tried to put it into flight. And they established an enormous tip jet test rig system down in the corner of the airfield at White Waltham. It was quite a fun place to work, actually, because you made so much damn noise, they kept you miles away from anybody else. So what you had was two chambers where you could actually clamp a pressure jet in as a test bed and run it in the chamber. You also had another system where you ducted air out to a rotating rig. So you had one rotating rig and two tip jet chambers, and you could do all this test bed running down there. And of course it could be done in a fairly safe fashion without having to go into the air with it. So you didn't have all the constraints of aircraft design.
Ultimately, the combustion chambers were built from mnemonic 80 with a liner made from mnemonic 75. Air entered the chamber from the rotor blade where it was mixed with atomized fuel. Once ignited, the mixture burned on its own until fuel was cut off. Test rigs at White Waltham were used to develop the tip jet systems for the Gyrodyne and the Fairey Ultralight, and new test rigs were built there for the Rotodyne project. Additionally, a second ground installation was established at Boscombe Down. This consisted of a rotor, power plants and controls for the Rotodyne. It was used for endurance testing and pilot familiarization. Before the fully assembled Rotodyne could take to the air, there was still extensive ground testing to be done. Fatigue testing had been extensive at White Waltham and Boscombe Down for the rotor system. However, there is more to building a helicopter than just attaching a rotor to an airframe. Helicopters are subject to structural problems related to the physical interaction between the airframe, undercarriage, and rotor systems. The entire aircraft would need to be ground tested to assess the interactions between these different structures. These ground resonance tests took place at White Waltham.
At the end of the day, the Rotodyne, albeit that it was quite a sophisticated and advanced machine, was a helicopter like any other. Vibration's a constant problem with helicopters, I'm sure you can appreciate. You stick this great rotating mass on top of the thing, and every time the rotor comes around, it puts a sort of puts some energy back into the aircraft. And one of the major problems that you've got in the design of any helicopter